All right, well, I'll get started here. We begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class. I just ask that you be glorified what we do, and that we just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so today we're talking about cardinality, and so I probably should begin with a definition here. And I suppose we talked about this a little bit before, but maybe we didn't. Two sets, A and B, are said to be equivalent. All right, they're said to be equivalent if and only if there exists a bijection between them. Of course, bijection is also called a one-to-one correspondence, right? Anyway, in this case, we say A is equivalent to B, like this with the two squiggles, all right? So it's easy to show that equivalence in this sense gives us an equivalence relation on the class of all sets. I have to be careful not to say the set of all sets, because then we get back into the trouble we talked about before, right? Like what about the set that contains all sets? Is that a set? So we don't want to get into that. So we talk about class of sets to avoid that. But indeed, this is an equivalence relation on the class of sets. All right. Now, for example, a very silly example that kind of dates these notes. This is a very silly example. But if I have A is the set containing 1, the empty set, and Dora, all right, and if I have B is the set containing the numbers 1, 2, and 3, then these are equivalent sets, right? Because I can easily say, well, phi of 1 is 1, phi of the empty set is 2, and phi of Dora is 3. You guys remember Dora the Explorer? You're that age, right? Yeah. So this is, of course, a very silly map, but nevertheless, these are equivalent sets, right? These are equivalent sets. Now, probably need to make another definition here. We're going to let n sub k to be equal to 1, 2, 3, all the way up to k for any k in the natural numbers, all right? So like in my previous example, my set B was actually what? N sub 3, right? So this is not like modular arithmetic or anything like that. This is just literally the list of the first k positive integers. All right. So my next example, which is a little bit less silly, suppose you have a set of k distinct items. We'll label them a sub 1, a sub 2, a sub k, right? And I could call this set, well, let's call this set A for lack of imagination, right? Then this set is equivalent to what? I'd say A is equivalent to n sub k, right? Now, in order to make good on that claim, I need to provide a bijection, a one-to-one correspondence between my set A and the set n sub k. What should that mapping be, guys, do you think? I'll use phi for the map, if that's okay with you guys. Phi of a sub, let's say a sub j, what should I let it be equal to? I want to make this like phi a mapping from my set A to n sub k, yeah? I'd like it to be a bijection. I'd like it to be a one-to-one correspondence, as we say. What should the formula be? What do you guys think? Any guesses? Yeah.
Just A equals J?
J, right. It is that easy, right? So if you do that, then it's fairly clear that phi is a bijection, right? We can prove it. Let's prove that this is a bijection. So if we have phi of, phi of x is equal to phi of y for x and y in A, right? Then there exists what? There exists, like, say, m and n in n sub k, such that x is equal to, a sub m, and y is equal to a sub n. Thus, phi of x is equal to a sub m, which is equal to a sub n, which is my phi of y, right? But what did we assume about this going into this whole discussion? We assumed that we have a set of distinct items, right? And what does that mean? That means if I have a sub m equal to a sub n, by definition of distinctness, we have m equals to n, right? Which then, of course, means what? Which then, of course, means that going back to the x is equal to y, right? So therefore, it's a one-to-one map. It's almost so silly, it's kind of hard to prove. How do you prove onto? Yeah. What do I do? Phi is a map. So this defines mapping. Or if you like, a function. So in order to prove equivalence of two sets, we have to come up with a bijection between the sets. We could use phi for it. We could use f, like whatever letter you like, really. Okay, so how about why is it onto? Like, what's the proof of onto? Work myself into a corner here. But if if j is in n sub k, then a sub j is an element of A, and phi of aj is equal to j. Thus, phi surjective. It's onto, all right? Which means it's one-to-one and onto, therefore it's a bijection, right? Alternatively, you could write down the inverse for this mapping and prove it's the inverse, right? What's the inverse for the map? Phi inverse of j equals to what? This is not hard. Yeah. A sub j, right. And you could check that that is in fact an inverse by composing both of them in the opposite order and showing that you get back the identity respectively on A and also n sub k, right? Of course, if we had that the inverse exists, that would also be a way to show that it's a bijection, right? Anyway. Okay, so this whole business about cardinality, it's all resting on the concept of a bijection, all right? So that's going to be a major part of our discussion, trying to find bijections between sets. The other major part of our discussion is going to be definitions, lots of definitions. So here's the other one. A set is said to be finite, all right, if and only if S, I should probably say a set S. If and only if S is empty, or S is equivalent to n sub k for some, I'm tired of my k, if you don't mind, I'm going to use an n sub n for some n in the natural numbers, right? So set is to be finite, if and only if it is in one-to-one correspondence with the empty set or with n sub n for some n in the natural numbers. And we define the cardinality of S to be S bar bar, which I have previously used number, and I'm going to use that again today. So I'm going to allow us two different notations, if that's okay with you guys. I'm going to use S bar bar for cardinality, but I'm also going to use number of S for cardinality. I think it's useful to have both notations, because I think number kind of more speaks to what it means, right? And where, how is this going to be defined? Where the, I'm going to use number for the most part. The number of the empty set is what? In other words, the cardinality of the empty set is what? And the cardinality of n sub k of n sub n is what? I'm sorry, my bad. I need to define it for S. So I need to put S in both of these spots and put a little bit of fine print over here. So it's going to be 0 when S is equivalent to the empty set, and it's going to be n when S is equivalent to the natural numbers up to n. All right. So like, for example, my example 1, the cardinality of A and also B was 3, right? And here the cardinality of A and 3, both were 3, because they're both, of course, in one-to-one bijection with n sub 3. N sub 3 is in one-to-one bijection with itself, right? You can always look at the identity map on n sub 3. You know what I'm saying? It's like n sub 3 is equivalent to n sub 3 because we can look at like psi of x is equal to x for x in n sub 3, and psi is a bijection. It's the identity map, right? So that shows you that any set is in fact equivalent. This generalizes, right? I mean, I did it for n sub 3, but we could just as well do it for any set. Take any set, right? It's going to be equivalent to itself because you can always look at the identity map from the set to the set, where you just map every element to itself, right? That's a bijection. In fact, we need that because I mentioned at the start of all this that this equivalence is in fact an equivalence relation on the class of sets. Part of that's reflexivity, right? So any set is equivalent to itself because we can write down the identity bijection. All right, so example 1, cardinality 3, cardinality 3. Example 2, cardinality k, right? Again, n sub k, cardinality k, right? Which is a formalization of what we mean by counting, right? The number of things in the set is the cardinality. Now that stops being, well, I mean, I guess there's room for some debate philosophically once you get past the finite case, right? Like, once we're talking about infinite sets, then, you know, can you count a number of things in an infinite set? Well, I'd say the best thing, I'd say yeah. And what we mean by that is the cardinality. All right, so cardinality is a way of extending counting to infinite sets. But we need to be systematic about that. So here we go. Next definition. What do you think we mean by an infinite set? I just used that word. What do I mean by it? A set S is infinite if what? Fill in blanks. I'll just give one blank for you. What should I put in that blank there? Not. Very good. Yes. An infinite set is one simply that is not finite. All right. So, let's see here. Proposition. All right. A set which is equivalent to one or more of its proper subsets is infinite. All right, probably it's helpful for me to like decode that sentence into some, into something more symbolic, right? Like, so if we have, let's say T is a subset of S, and T is not equal to S with T equivalent to S, then S is infinite. So that's what we mean by proper subset, right? A subset which is not the whole set is a proper subset. Right? So standard example of this, right, would be, like, this is one of the ways we can show the natural numbers are infinite. So let's see if we can come up with that. Example 3. So let's look at S equal to the natural numbers and T equals to twice the natural numbers, right? In other words, the even numbers. Yeah? So you guys tell me, what do you think the bijection is between these? What do we do? I'll use phi again. I want a bijection phi from S to T. What would that be? Phi of n equals to what? 2n. There you go. Right, if we have phi of n equals to phi of m, that implies that 2n is equal to 2m, which implies that n is equal to m. Thus, phi injective, right? If we have, x is an element of 2n, then x is equal to 2j for some j in the natural numbers. Thus, phi of j is equal to 2j is equal to x. Thus, phi on 2. Therefore, phi is a bijection. Right? Thus, phi is a bijection. And we have that the natural numbers are equivalent to twice the natural numbers. All right. And then by the proposition above, what does this mean? Let's think about it. So we have 2n is a subset of n, right? With, of course, 2n is not equal to n. Therefore, n is not finite. Right? In other words, n is infinite. Are we good? Now, can you guys think of another way we could prove that n is infinite? They're really kind of like two major paths to go down here to show a set's infinite. Like the one is what we just did, which is to find a proper subset, which is a one-to-one bijection with a set, right? Yeah.
We could assume it's finite and then show that that's a contradiction.
Ah, very good. Yeah, so assume it's finite, right? Assume n is finite, then there has to be a largest element, right? But then by the successor property, which is intrinsic to the definition of natural numbers, add 1, right? So that largest number plus 1 is not in there, therefore it's not finite, right? Because we contradict that the largest number is the largest number by just adding 1, right? This kind of goes back to like arguments you might have had as a child with other children since you're in this class, right? Arguing about who's got the bigger infinity, that kind of thing, right? Like I got the largest natural number. Oh, really? Well, I'll take double that number, or I'll add 1 to it, or I'll square it. Or, you know, as you learn more arithmetic, you do more things to the infinity that you're imagining. But yeah, I remember vaguely having arguments with like neighbor kids about like what the biggest number was, and I vaguely remember a conversation with my next door neighbor about like Googleplex, and this is long before Google. All right, this is the 80s. The internet only existed in like government labs at this point, right? But anyway, it was just a twinkling in Al Gore's eye. Let's see here. I'm sorry, that's a dated reference to a. Anyway, okay. Countably infinite sets. Definition. This is the definition of denumerable. All right. Let S be a set. All right. We say S is denumerable if and only if S is equivalent to the natural numbers. Moreover, the cardinality of such a set is said to be aleph naught. Right. Aleph naught is the cardinality of the natural numbers. Right. So here's where it starts to get weird. Because what I'm telling you is that the cardinality of the natural numbers and the cardinality of the even numbers is the same. Yeah? So like, the number of the natural numbers is equal to the number of the even numbers, right? Because they're in one-to-one bijection. We just proved that, yeah? Which means that they're equivalent as sets. Which means that they both have cardinality aleph naught. What else do you think has cardinality aleph naught? I mean, something obvious I think that you guys might guess would be like positive odd numbers, right? And if you have a little bit more imagination, it's not hard to believe that the cardinality of the integers probably would be the same, right? Surely we could come up with a mapping that's one-to-one between the natural numbers and the integers. How would you do that? Yeah?
You could like map every even number to a positive integer and every odd number to a negative integer.
So you're like psi of x is equal to, what did you say? X if x is an element of z and x is, oh, I'm sorry, we're doing for n. X is element of n, to n, right?
Yeah, and then you can map to a negative number, and then if x is an element of 2n plus 1, it can map to a positive integer.
Oh, this one?
I guess.
Would that make psi a mapping from n to z. That's almost it, but we need to like manipulate, right? Like, yeah.
Negative 1 over 2x, and for x is the element of,
Let me modify. I'm going to put it down here. F of x. What's your formula?
so for x is an element of 2x, negative half x, negative x over 2.
Negative x over 2.
And then
I should put 2n minus 1 here, right? Because the natural numbers are equal to the evens unions with like twice the evens minus 1. I have to take away 1 from 2 to get back to 1, you know?
then x minus 1 over 2.
X minus 1 over 2. So if I put in 1 into that, I get 0. If I put 3 into that, I get 1. If I put 5 into that, I get 2. I think this will work, yeah. So like what we're doing is we're like taking the even number and dividing by 2 to make it, you know, just. So this gets 0. This gets 0 in all the positive numbers, and this gets the negative numbers. Basically what we're doing, just to like illustrate it sort of like graphically, you're taking the, so like here's the natural numbers, right? And we're taking 1, and we're mapping it where? We're mapping 1 to 0. And then we're taking 2, and we're mapping it over to, mapping 3 to where? To 1, right? We're mapping 5 to 2, like that, right? And then we're taking the 2, and we're mapping it over here to minus 1. And then we're taking the 4. I'm not sure my picture is super helpful, but this is kind of a picture of what's going on with the formula. We're just taking all of the even numbers and relocating them to the negative integers. We're taking all the odd numbers and relocating them to the positive integers. And we can just complete this process, right? Like just, and it just keeps going. So that shows you that f is in fact a bijection from the natural numbers to the integers. So therefore, if you'll forgive me if I don't prove that this is a bijection, I mean, we've done a few proofs today. I think it's clear you could work out the proof, right? So therefore, the natural numbers are equivalent to the integers. Very good. So did you guys have a chance to watch the video that I linked last Thursday? Both of them? Very good. Okay. Sorry I didn't notice the coffee the other day, by the way. I'm generally impervious to jokes during class. If I make a mistake, I only see the mistake, you know. All right, so there are endless examples to this, right? Like the fiber of sine. If we, this would be equivalent to the number of the inverse image of sine of 0, right? This right here is what? This is, you know, x in the reals such that the sine of x is equal to 0, right? But we learned in trigonometry that that's n pi, such that, you know, n is an integer, right? So in other words, this is pi times the integers, right? And once you see that you've got pi times the integers, it probably becomes somewhat obvious how to write a bijection between that and the integers, right? You just do like phi of, you know, like f of x is equal to pi x. That will give you a bijection from that set I just wrote, the 0 set of sign, to the integers. All right. But this is where I think it starts to get, I mean, there's lots of other things that are weird. You can add things to like this. Any Cartesian product, like if you take a Cartesian product of the natural numbers with itself, n cross n, those are also in one-to-one correspondence with n. Or you could take a finite k-fold times. Still, this is a denumerable set. Its cardinality is just aleph naught. All right. Now there, it starts to get a little bit more challenging to think about exactly how would you write down the bijection, right? It's a little bit more challenging. I'm not going to try to do that this morning. One thing I should, though, also mention is, well, we should talk about the rational numbers, right? What do you guys think? Rational numbers? Is the rational numbers as a set, is this larger? You think it's, what do you think? Is it larger than the integers? I mean, I would think so. Personally, I would be shocked, honestly, if the rational numbers were not larger in size, right? Larger. So when we talk about size of a set, colloquially, that almost always means cardinality, right? As you go on in mathematics, there's other descriptions of the character of a set which are related but different. Like in linear algebra especially, we'll talk about the dimension of a set. Or in calculus 3, we'll talk about the dimension of a set. Right? You have a surface, you have a curve, like a surface is two-dimensional, a curve is one-dimensional, a volume is three-dimensional, and so forth. And there's a distinction that should be made between dimension and cardinality usually. These are not the same thing. I would say that's one of the fundamental confusions of linear algebra that 321 seeks to clarify. It's not a big deal, but anyway. So what do you guys think? Rational numbers. Well, I mean, so like the thing about rational numbers, if I have, say, a over b and c over d in the rational numbers, yeah? Then notice that if we take a over b plus c over d and we divide by 2, right? This gives us what? Like, can't do math here. Is that AD plus BC over 2BD? Is that right? Do the math, right? My point to you is that is, again, a rational number, right? So on the number line, if we put a over b here, and we put c over d here without loss of generality, suppose they're in this order, well, in the middle, right, there's this number x. Yeah? I'm calling this thing x, right? So what I'm telling you is between any two rational numbers, there's another rational number, right? That's a lot of rational numbers. That's not true for integers, right? That's a genuinely different property. Integers aren't like this. You give me two integers, is there another integer between those? Not necessarily, right? If they're successors, there's nothing in between. So there's something very different about the rational numbers and the integers. And so this is why when Cantor proved that the rational numbers are denumerable, it's kind of surprising. All right? And I don't, there's some things in math I feel like I would have come up with, maybe, if I was left to my devices. Maybe I could have come up with it. This is not one of those things. And this is not in my notes, unfortunately. But I will attempt to draw the picture. So, like, here's the deal. You let Q equal to, let's say A over B, such that A and B are integers, and the GCD of A and B is 1. All right. In other words, like, let me put it into words. We want this to be a fraction in, I guess we usually call it like lowest terms. So like, we won't write 3/6. No. Instead, what is it? 1/2, right? We don't have, 17 over 51. We have 1/3, right, etc., right? So if you put fractions in their, like lowest terms, then it's possible to order them. It's possible to put them in an ordering. And I just so happen to have the picture here. Oh man. Oh, wait a minute. Oh, I was fished in. Well, this is actually the bijection between the n cross n and n. I guess I'll just give you guys this one. Oh well. Like I said, I wouldn't have thought of it, and it's not in my notes, and I'm a little short on time at this point in the semester, guys, to be totally honest with you. So I didn't have a chance to pin down this mapping, but there is an explicit mapping between the integers, between the natural numbers and the rational numbers. Of course, if you can do it, think about this. If you can do an explicit one-to-one bijection between the natural numbers, then guess what? You could also do an explicit one-to-one bijection between the even numbers, or between the odd numbers, or between the integers, between any of these things, which has the same cardinality. Because to say they have the same cardinality, to say they're equivalent, is to say that there exists a bijection. And we have proved that the composition of bijections is bijections. So if I can get from point A to point B, and if I get from point B to point C, I can also get from like point A to point C, So it's somewhat immaterial whether we talk about a bijection from the natural numbers or the integers, let's say. But the picture that's in this, I like this book a lot. It's the Proof, Logic, and Conjecture Mathematician's Toolbox by Wolf. But here's the kind of picture he has for the, all right, so like n cross n is this grid of points, right? So we can visualize the natural numbers Cartesian product with itself as the so-called lattice of, positive integer coordinates. Yeah, like this. So what I'm drawing in blue, or trying to, is a picture of n cross n, right? And so what's the bijection? It can kind of be pictured like this. We go here, then we go there, and then, whoa, be careful. We go back down to here like that, and then we go over here like this. All right. So let me tell you what I'm saying. I'm saying that psi of 1, 1 is 1. Psi of 1, 2 is 2. Psi of 1, oh my bad, psi of, yeah, okay, I'm fine. Psi of 2, 1 is 3. So you go 1, 2, 3, and then you go back this way, up here, like that, all right? And then kind of go up here to the next one, and then you go back down, doot, 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 and then you go over here to the next one over, like so, doot, and then go back up, doot, 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 and this continues, as you can see, right? Ziggy zaggy, forever and ever, amen. This will cover, right? Etc. This is how we can form a bijection between the natural numbers cross the natural numbers and the natural numbers, right? Now, I'm not going to prove fully that this works, but I think you can see it's plausible, right? We're definitely going to hit every possible natural number if we continue the zigzagging. And it's fairly obvious that it's a one-to-one map. Therefore, it's a bijection. Therefore, the natural numbers Cartesian product themselves have the same cardinality as n. This is yet another denumerable set. And what I was getting to, and I don't have a picture, unfortunately. I'm sorry, guys. I thought this picture I was looking at in the book was explicitly the map for Cantor. It's not. But if you think about it, if you have the fractions in lowest terms, you could arrange them in a grid like this, right? You could list them in this kind of grid, and then you could do the zigzag path on the lowest term fractions, and that's Cantor's map. That proves that, in fact, yes. And this weirds me out, but it's true that the cardinality of the rational numbers is also Aleph naught, right? But you know, if you can do these things once, guess what? What's the cardinality of the rational numbers? Cartesian product, the rational numbers. It's again Aleph naught because of exactly this argument. So we could just as well, do the same kind of thing for rational numbers if they're, anyway. So that's also true. So basically, taking finite Cartesian products okay. Let me move on here. So definition. If I can, I better erase. Because we don't need this stuff anymore. One more homework to go in here, guys, right? Phew, the end is near. It's upon us. So, definition. A set S is said to be countable all right, if and only if S is finite or denumerable. Denumerable is like a really just fancy word for saying it can be enumerated, which is to say it can be put in one-to-one bijection with the natural numbers. All right, that's the origin of the term, I believe. And if a set is not countable, it's said to be uncountable. All right. Sometimes denumerable is also called countably infinite. Right, so that's another turn of phrase. This is equivalent to countably infinite, which kind of makes sense, right? Because it's an infinite set which is countable. So, all right. Now, yeah. So that brings us to the next theorem. And this one, this one I will not prove today. All right. This one, I think this is really the one that Cantor, this is the deeper result of Cantor. The open interval 0, 1 is uncountable. All right. And so to put it more bluntly, 0, 1 is not equivalent to the natural numbers, right? Which we could express like this, right? What's this mean? This means that there does not exist a bijection, let's say G, from 0, 1 to the natural numbers. There is no such bijection. That's what that means. The proof of this is formidable. All right, so I gave you guys a PDF in the announcement I made last night. If you read that, there's actually a pretty accessible presentation of the argument that Cantor made, which is also in that video I sent you last Thursday, right? This is that place where he had to use the axiom of choice in order to set things up. It's subtle. And perhaps we'll do that next class, all right? But I want to focus more kind of on the easier tier of things in here today. So, all right, definition, the number of 0, 1, the cardinality of it, if you like, in my other notation. Like my notes, again, I'm using the bar notation in my notes. My apologies, I didn't have a chance to like just edit all of the notes and change all the bars to numbers. I just didn't have time, and I was worried if I tried to do it in a pinch, I was going to miss some, and then we'd be confused. So I figured it's better just to use two notations as opposed to like, yeah. Anyway, so cardinality of 0, 1, and this is equal to C, and that C is for continuum. Continuum, all right. Sometimes people will say C is aleph 1. Writing C equals to aleph 1 is essentially the continuum hypothesis. Because that notation, what that notation suggests is that aleph 1 is the next infinity past aleph naught. And that is the continuum hypothesis. The continuum hypothesis is the conjecture that there is no infinite set which has a different cardinality between the natural numbers and 0, 1. Or as we'll soon discuss, the cardinality of 0, 1 is the cardinality of the real numbers. So like whatever infinity there is to describe the size of the natural number, whatever infinity there is to describe the size of the real numbers, the continuum hypothesis says there can be no other between those. That's it, as I understand it. Now, if I'm wrong, let me know. This is not my, my wheelhouse. Okay, anyway, so I just claimed that, well, let me make a claim. And then I'll try to back up the claim with some mappings. 0, 1 is equivalent to like AB. And this is in fact equivalent to minus infinity to infinity, all right? So I'll start out with AB. So f of x is equal to, I want a bijection to AB. So what I would do is I would do A plus, parentheses, B minus A times x. Check out how that works. If I plug in 0, right, I would get A. If I plug in 1, I would get B. Of course, I don't actually do that because 0 and 1 are not in the domain if we're talking about f as a mapping from 0, 1. But likewise, neither are A and B, right? So this, as long as B is not equal to A, is an invertible map, right? So I'm not going to show you the details, but you can argue this is a bijection, all right? And since that's a bijection, that proves that the open interval 0 to 1 is in fact equivalent to any other open interval, all right? So how about this? If we look at, show you the inspiration for what I'm about to tell you. This is the graph of what function? I suppose we're currently in example, man, what example are we in? I don't know. 4, 5, 6, I can't remember. I declare this to be example 5. I declare this to be example 6. All right, there we go. Don't say I didn't do any examples today. So that's the graph of tangent, right? Y equals tangent. In pre-calculus, right, we essentially show that the tangent of minus pi over 2 to pi over 2 is minus infinity to infinity, yeah? And guess what? The inverse tangent is defined, right? I mean, this tangent from minus pi over 2 to pi over 2 is strictly increasing, right? It is a one-to-one function. It's also onto, right? So tangent is a bijection, right? If we say, f of x equal to tangent x, then f is a mapping from, if we, well, to be clear, for x an element of minus pi over 2 to pi over 2, then we have f is a mapping from minus pi over 2 to pi over 2 to the whole reals, right? And this is a bijection, right? So that shows you, right, that we have 0, 1 is equivalent to minus pi over 2 to pi over 2. But then by the tangent function, it's equivalent to minus infinity to infinity. So this shows you that the cardinality, right? What's the cardinality of the real numbers? It is the continuum, right? All right. My example 8.3.5 is like most of the things I've written today in terms of maybe not this example over here. This is a little bit sneaky, but the natural n cross n thing. None of these even approach the what's the word? The mathematical shenanigans that is implicit within the next example. Like the construction here, to me, this is one of those things, like I don't think I would have come up with this personally. So it's one of those things you need to pay attention to because you're going to need to more or less modify this idea for one of your homework problems. And I don't think you're going to get that homework problem unless you pay attention to this. I really don't. At least I wouldn't. So here's the thing. Example 8.3.5. We're going to show that the closed interval from 0 to 1 is equivalent to the open interval from 0 to 1. So the reason that this is hard is the things that you're used to won't work. All right. We have theorems in analysis, as we'll talk about soon. Maybe I've talked about them already here. I don't think. But if we have a continuous function, one of the things about a continuous function is that the inverse image of open sets is open. All right? The inverse image of an open set is open for a continuous function. So if I had a continuous mapping from this set to this set, the inverse image of this open interval 0 to 1 would have to be that, the closed interval 0 to 1. Well, that's a problem because the closed interval from 0 to 1 is not an open set, as we could define it. What that means is whatever example we're looking for, whatever function we're looking for, it's not continuous, which means that it's something weirder. All right, and well, here's the construction. Now there is another way to prove this with a theorem that we'll talk about shortly, but if we have to construct the bijection directly, it is a rather formidable task. And your homework, I have you do it two ways. I have you do it mimicking the construction of example 8.35, and then also with the theorem, the so-called CSB theorem. Probably can say their names. Cantor, Schroeder, Bernstein theorem. I may get to it anyway. So it's 1/2 if x is equal to 0. It's 1 over 2 to the 2 if x is equal to 1. All right. It's 1 over 2 to the n plus 2 if x is equal to 1 over 2 to the n for some n in the natural numbers. And let's see here, it's x otherwise. And so here we're going to define f as a mapping from 0, 1 to the open interval 0 to 1. Let me see if I can try to draw a picture of what this is. Maybe that will help. I don't know. So here's 0. Here's 1, right? Where's the funny business going on? Down here is the open interval from 0 to 1, all right? How does this map work? It's 1/2 if x is equal to 0. So we're taking this 0 and we're mapping it to the halfway point. Right? It's 1 over 2 squared if x is equal to 1. So that's also known as a quarter, right? That's this one. All right. Then it's 1 over 2 to the n plus 2 for x equals to 1 over 2 to the n. So basically, let me draw those as like, all right, so there's like the half, right? Where's this start? 1/2, 1/4, right? 1/8, 1/16, etc. And all of those are mapping to like the next one down, right? And then right? So like all of this is getting mapped down to there. So the idea of this map is to select a particular subset of 0 and 1, right? And to sort of manhandle that subset onto itself using the fact that it's a countably infinite set. So like if you shift, you're still going to the same subset because the distinction and the shift gets sort of lost in the infinity in the way that you're, again, we're taking the endpoint, shoving it to here, the other endpoint, shoving it to here, and then the rest of this, and then we're taking this countable sequence, denumerable sequence inside 0, 1, and we're mapping that to the rest of it. That's the idea. And otherwise, x maps to x. So if you sort through it, this does in fact define a one-to-one map, and it's also clearly onto. I say clearly, but that might be a bit of a stretch. The reason it's onto, right, is it hits everything of the form 1 over 2 to the n, right? Because it covers 1/2 and 1/4 from the 0 and the 1, and then the rest of the things of the form 1 over 2 to the n are mapped to by the rest of these. Everything that's not of the form 1 over 2 to the n in 0 to 1 is mapped to by x, right? Otherwise, the mapping is super boring. It just takes x and it maps it to x, all right? Yay.